Welcome to this explainer. Today, we are going to trace the absolutely fascinating, totally invisible journey of a pill from its very origin all the way to its biological exit. Every time you swallow a tablet, you're kicking off an incredibly complex chain reaction inside your biology. So today, we're unlocking the science of pharmacology to understand exactly how that happens. Okay, let's dive into this. Here's our roadmap for today. We're going to cover Section 1, the blueprint, Section 2, decoding drug names, Section 3, entry strategies, Section 4, the body's role, and finally, Section 5, the drug's role. Section 1, the blueprint. What is a drug? Now, what's really interesting about this slide is how ordinary it looks, right? We've all seen a colorful pile of capsules like this in our medicine cabinets. But behind these bright colors is a highly precise science. We often take for granted what's packed inside these tiny capsules before we casually toss them back with a glass of water. And that brings us to our core definition. Pharmacology isn't just about handing out pills. It is the overarching, comprehensive science of how drugs interact with biological systems. It covers the mechanism of action, the uses, the adverse effects, and ultimately, the final fate of that drug once it crosses the threshold into a living, breathing body. But wait a second, are drugs and medicine actually the same thing? Well, not exactly, and this is a subtle but absolutely crucial distinction. A drug is broadly defined as basically any substance that affects the function of living cells. A medicine, on the other hand, is a drug that's specifically used to prevent or treat a disease. So, while all medicines are drugs, not all drugs act as medicines. Make sense? So, where do these substances even come from? You might think they're all just cooked up in some sterile lab somewhere, but our sources are incredibly diverse. We literally mine them from the earth, like minerals from magnesium sulfate. We extract incredibly powerful substances like morphine straight from plants. Yes, we do have synthetics like aspirin, but we also rely on microorganisms for things like penicillin. And we even use cutting-edge genetic engineering for human growth hormone. It's like the entire world is our pharmacy. Section 2, decoding drug names. What's in a name? If you've ever felt completely confused staring at the pharmacy aisle, you are definitely not alone. That's because one single chemical substance actually carries 3 distinct identities, just depending on who's talking about it. Every single drug has a chemical name, a generic name, and a brand name. So the crucial point is understanding the difference between the names you actually see on the box. The chemical name, like N,4-hydroxyphenylacetamide, is highly complex. It's really only important to chemists. What we everyday users need to know is the generic versus the brand name. The generic name is the universally accepted, official, non-proprietary name, like acetaminophen or paracetamol. There's only one generic name per drug across the whole globe. The brand name, though, that's the copyrighted proprietary name chosen by a specific manufacturer. Think Tylenol or Panadol. So one single drug can have multiple brand names, but that underlying generic substance is exactly the same. Section 3. Entry strategies. Drug administration. All right, let's move from the bottle to the body. How do these drugs actually get inside us? Well, the most common way is the oral route, swallowing it so it travels through the stomach and intestines. The pros here are pretty obvious. It's safe, incredibly convenient, and economical. But it comes with major biological hurdles. The onset of action is slow because, well, it has to be digested. Some drugs get completely destroyed by your stomach's gastric acid before they can even do anything. Plus, if a patient is experiencing severe vomiting, this route just isn't going to work. Now, compare that to the intravenous or IV route. Here, the drug is injected straight into a vein. This completely bypasses the entire absorption process we just talked about. Because it enters directly into the blood, the action is incredibly rapid, and doctors can give large, very precise doses. But that efficiency leaves very little room for error. The huge disadvantage here is that once that drug is injected, its effect cannot be easily stopped. There's really no going back, which is exactly why it requires significant medical expertise. Section 4, Pharmacokinetics, the body's role. And this brilliantly illustrates the central tension of pharmacology. You see, it isn't just a drug fixing a body. It's a highly dynamic, two-way interaction between the chemical structure of the drug and the complex biology of the human body. They are actively fighting and acting upon each other simultaneously. To make sense of this two-way street, scientists split this interaction into 2 complex concepts, pharmacokinetics and pharmacodynamics. They're 2 sides of the same coin. Simply put, pharmacokinetics is what your body does to the drug. Pharmacodynamics is what the drug does to your body. let's start by looking at the body's role. Your body basically treats the drug like a foreign invader and puts it through a rigorous four-step biological assembly line. First is absorption, getting the drug into your circulation. Next is distribution, which carries it through your blood to the rest of the body. Then comes metabolism, where your body actively breaks the chemical down. And finally, excretion, where your body flushes it completely out of your system. Because of this intense biological gauntlet, we have to talk about a concept called bioavailability. This is the proportion of the dose you took that actually reaches your systemic circulation. Think back to that oral route. If a drug is partially destroyed by stomach acid, its bioavailability drops. So taking a 100 milligram pill does not mean 100 milligrams actually makes it into your bloodstream to do its job. And we can actually map out the lifespan of this drug's effect over time. The onset of action is how long you have to wait before you start feeling relief. The peak effect is when the drug is working its absolute hardest. And the duration of action is the total amount of time the drug keeps working before your body inevitably metabolizes and excretes it. Speaking of excretion, how quickly does the body clear this stuff out? Well, we measure this using something called half-life. This is the time required for the concentration of the drug in your plasma to decrease by exactly 1/2 of its initial value. Drug half-lives vary wildly. Some are super short, some last days, and this is the exact metric that dictates whether you need to take a pill every 4 hours or just once a day.
Section 5, Pharmacodynamics, the drug's role.
Let's move to and see how this builds into the other side of the coin, pharmacodynamics, or how the drug attacks the body. Drugs generally interact with receptors in our body, and there are two main types of interactions you need to know: agonists and antagonists. Think of it like a lock and key. An agonist is a working key. It binds to the receptor, successfully opens the lock, and produces the desired therapeutic effect. An antagonist, however, is like a broken key. It fits into the lock and binds to the receptor, but it produces absolutely zero response. By jamming up that lock, it acts as a blocker, completely preventing other drugs or natural chemicals from getting in and having an effect. And that brings us to the end of our journey today. The next time you look at those colorful capsules, you now know the incredible dynamic science packed inside them. So I leave you with this to ponder. Next time you open your medicine cabinet, ask yourself, is the chemical inside this bottle acting as a key to start a process in my body or a blocker to stop one? Thank you for exploring this with me. Keep asking questions and keep learning.